tappings. These are HV terminals. These are LV terminals. Tappings are mainly provided on HV side only. These are the tap positions. This is off circuit tap changer. HV windings are split into two parts. 1, 2. All three phases are split into two parts. These are the tap positions 3, 4, 5, 6, 7, 8, 9, 10. So this is a switch position or tap position. For any variation in primary voltage, the secondary voltage has to be maintained constant. Throughout this range, the voltage remains constant. P is the nominal tap position. We are assuming that at nominal position tap 3, the primary voltage is 11 kV and the secondary voltage is 433. For some reason, the voltage has increased to 11 to 75, then the secondary terminal voltage must be maintained at 433 only. From this transformation ratio K, V2 by V1 equals to N2 by N1. Here N2 is constant, N1 can be varied, and V2 we have to maintain constant. V1 is varying as per the supply voltage. So here, in order to maintain V2 by V1 as constant and N2 by N1 as constant, as supply voltage on the primary side increasing, we have to increase the number of turns on the primary. During terminal tap position 3, the HV lead connections are at 5 and 8. This is 5 and this is 8. These two are connected. Now the HV voltage is increased to 11 to 75. So now we have to change the tap position to 2. That means 7 and 5 has to be connected. So at tap position 3, the connections are 5 to 8. Now we have to move to tap position 2. That means we have to connect 7 and 5 leads. This is 7 and this is 5. We have to connect these two leads. That means we are adding this portion of winding to the circuit. That means when the terminal voltage on the primary side increases, we are increasing the primary turns. As V1 is increasing, we are increasing number of turns on the primary side. So the K ratio V2 by V1, N2 by N1 is maintained constant. The other case, if the terminal voltage is decreased to 10725, then we have to change from tap position 3 to tap position 4. That means we have to connect terminal leads 4 and 8. So at tap position 3, the terminal connections are 8 and 5. Now the voltage has decreased, so we have to move to tap position 4. Now the new terminals are 8 and 4. 8 and 4. So as the terminal voltage decreases, we are removing a portion of winding. So as the terminal voltage, primary terminal voltage V1 decreases, primary side number of turns has to be decreased. So when the primary voltage increases, we are increasing the number of turns on the primary side. When the primary voltage decreases, we are decreasing the number of turns on the primary side. So by doing this, we are able to maintain K ratio as constant. In steps of 2.5 means here each portion is equals to 2.5% of total voltage. The total voltage is 11 kV. For this, 2.5% voltage will be 275. For 275 voltage, this winding equal to 275 voltage. And the voltage variation is plus 5% to minus 10%. So plus 5% means it is up to 11,550. Minus 10% means 990 volt. This is with reference to 11 kV. So from 11 kV plus 5%, we have to go in 2.5 steps. In 2.5 steps means we require only 2 steps. From 11 kV to 990, we have to go in 2.5 steps. Then here we required 4 steps. 1, 2, 3 and 4. So from 11 kV, we have to increase 275 volt every time and we have to reach plus 5%. And from 11 kV, we have to decrease 275 volt in every step, and we have to reach 990 volt. So for this arrangement, we require total 7 tap positions, and these are the connections for tappings. So the concept is same. As the primary voltage increases, we have to increase the number of primary turns. As the primary voltage decreases, we have to decrease the number of primary turns so that we can maintain A ratio as constant.